Welcome to Manimated AI. From Netflix to math class, systems are everywhere. Today, you'll see we will uncover what linear systems really are. But first, let's understand what a system is. It takes an input, does something to it, and gives an output. Some systems are linear. You can add up to make new solutions from existing solutions. That's one of the property of linearity. But what does linear mean? We'll understand it later in the video. Let's look at some everyday systems. Each of these: Netflix, music apps, even games. Take an input, apply a rule, and give an output. Netflix takes your watch history and recommends movies using matrix operations, a classic example of linear systems in action. Music platforms analyze your liked songs and use linear similarity scoring to suggest tracks you might enjoy. Even games respond to your controller actions by using linear transformations to animate objects on screen. Think motion, rotation, and physics. So while these applications are complex, their underlying behavior often begins with linear systems. Simple, powerful, and predictable. So, what does linear actually mean? Let's find out. We've seen how systems can behave in linear ways. But what exactly does linear mean? Let's break down what makes an equation linear. Just simple terms, constants multiplied by variables, like this. Do you know which equations are considered linear, and which are not? Let's break it down. A linear equation is one where every term is constants multiplied by variables. These are all linear equations. Now, can you guess which of these are not linear? May have variables raised to powers other than 1, equation that does not form a straight line. Why are these nonlinear? Powers, logs, sines, products of variables, all break linearity. Let's understand this with the help of graph. Here's the difference. A linear equation forms a straight line, predictable and smooth. Let's solve this equation for y. That helps us treat x as the input and see how y reacts. But a nonlinear equation like x squared curves away, breaking that linearity. Let's look at another example. 5x minus 2y equals 8 is still an equation, not a function, and it is a straight line. Clearly linear. This is an equation, not a function. But if we solve it for y, we can treat x as the input and y as the output. Solving the equation gives us y equals 2.5x minus 4, a linear relationship. But y equals cosine x? That's a curve, periodic and nonlinear. Let's understand what makes a system linear. Let's start by explaining why the term is linear. For example, let's use the term 2x minus 3y. If you have two pairs of x and y, say x1 by 2 and y1, y2, and we have to sum up the results, and combining like terms. When we group the x terms together and the y terms together, this shows that the system respects additivity. One of the key properties of linear systems, if we use these terms as input, the output would same as above. Let's see how. We can easily open the brackets back and return to the same expression. That's what makes it linear. It's stable, additive, and preserves structure. Now let's understand which and why terms are nonlinear. Here's the first nonlinear example. We have x1 square plus y1 and x2 square and y2 separately, and then try to combine x terms and y terms together. We know that when you square a sum, you get extra terms. Let's understand what happens when we expand x1 plus x2 the whole square. When we expand, we get x1 square plus the extra term 2, x1, x2 plus by 2 square. Middle term wasn't in the original. So this proves nonlinearity because when added it cannot go back to its original equation. Now here's another nonlinear example. You might think that sine of x plus y is the same as sine x plus sine y. But that's wrong. When you open up the bracket you get sine x times cosine y plus cosine x times sine y. This is called the sine addition formula. It shows that sine doesn't just add. You can't go back to the original form. That's why sine is nonlinear. Now, let's see how it looks in general form. To summarize, a linear system takes each input, applies a constant weight, and adds the results. So how do we express that, when there are many inputs and many outputs? On the left, we have the input vector x and the system matrix A. Together, they produce this output, a new vector made of weighted combinations of x. Multiply values from a and x. This gives us the intermediate sums, 8 plus 1 and negative 4 plus 3. And finally, we simplify the sums so a times x gives the output vector 9 and negative 1. Let's understand this with an example. We make decisions every day. How much to work, how much to rest, but behind those choices is a quiet logic. Let me show you. Meet our student. He has 12 hours a day to split between studying and playing. He loves both, but he has to use those 12 hours wisely. Now, here's the catch, his mom uses a score to track him. Each hour of studying gives him 5 points. Each hour of playing deducts 2. To keep mom happy, the total score must be exactly 22. He has to decide if he wants to make his mom happy, sad, or neutral. Let's define our variables. Let x be the number of hours spent studying, and y be the number of hours spent playing. Let's plot the equations x plus y equals 12, and 5x minus 2y equals 22. Let's draw both equations on a graph to find where they intersect. Let's solve the system. From the first equation, we find x equals 12 minus y. Then substitute into the second equation. Distribute 5, 60 minus 5y, subtract 2y, and set it equal to 22. Combine like terms, negative 7y equals negative 38. Solving gives y equals 38 over 7. That's about 5.43 hours of play. Now substitute back to find x. That's about 6.57 hours of study. This is the intersection point, where the student keeps mom's mood neutral. This is how you use linear systems without even knowing about it. Remember this video? We turned inputs into outputs, explored lines versus curves, saw additivity in action, and solved them with matrices. From mystery to mastery, next we will uncover eigenvalues and eigenvectors, what they are, why they matter, and how to find them with visuals that make it click. Thank you for watching. Don't forget to like, share, and subscribe, and we will see you in the next episode. Stay tuned. This video is made by Astha Joshi. Keep learning, and I'll see you in the next video.